I have my real milk instead of oat milk again, so I'm back in a good mood. All right. So for today, uh, I asked you to read the MapReduce paper. And so this is a bit of a shift in topic for us. So I want to try to, before I jump right into talking about MapReduce, I want to try to contextualize it a little and relate it to things that we have been talking about. So until now, we've been talking a lot about systems that you make requests to and you get responses from. So the key value store that you're implementing works that way. Dynamo works that way. And a lot of systems work that way. So web servers work that way. Databases work that way. Whoops, I have to fix one thing on Zoom here. What do you see if you're on Zoom right now? Can you see my paper? You have OBS? Okay. 1 second. Fascinating. All right, how's this? All right, I must have shared the wrong display. Sorry about that. All right, onward. So yeah, so as I was saying, so up until now, we've been talking mostly about systems to which you make requests and receive responses. So the key value store that you've been working on, or any key value store, falls into that category, or web servers, or databases, caches that might sit in front of web servers or databases. All these things fall into this category of systems to which you make requests and receive responses. So we can lump all these things together under the term services or online systems. And note that some of these things can be quite specialized, right? So when you see web servers here, you shouldn't necessarily think just about like a general purpose web server like Apache or Nginx. You should think about something that, like an app that might have its own integrated web server that's built specifically to serve only that app. So there's a lot of things that fall into this category. And what all these have in common is that they wait for requests to arrive from clients, and then they try to handle those requests quickly. Quickly to the extent possible. Quickly within the constraints of, say, whatever consistency model that you're trying to guarantee and so on. But low latency is important. The time between when you send a request and when you receive a response. Availability is typically important. Every request receives a response. Usually, that's important. But this is not the only way of building systems. And there are also systems that that take in a large amount of data, do something to process it, and produce some output data. And this might take quite a while. So that's a different kind of system, and we call these systems batch processing systems, or offline systems. So the main performance concern with these kinds of questions is not low latency. It's having high throughput. So the more data that you can process at a time, the faster that you can crunch through a huge data set, that's the goal with these kinds of systems, batch processing systems. So which is MapReduce? Is it an online system or is it an offline system? Right, yeah, it's an offline system. So although Google obviously runs a lot of online systems too, under the hood, the data that those systems are serving up, which might be search results or videos and so on, was most likely the result of some large-scale, offline, distributed data processing job. So, and typically that work would have been done not necessarily by MapReduce, more likely by a system that was a successor of MapReduce, but something that was in the spirit of MapReduce often. So MapReduce falls into this category. And its successors. So MapReduce is old now. It's now 15 years old. It's no longer the shiny new technology that it once was. Somebody just asked in chat, so MapReduce is dead. So I would say that it's not so much dead as there are systems that now do the same thing, but in a more general way. So there are systems that generalize MapReduce. The ideas are still good, but the system has been subsumed by something that is perhaps more general or smarter. So I think it's still worth studying and understanding the original MapReduce paper. One, because it's a well-written paper and it's a classic, and also it helps us see why and how batch processing is important and useful. So we're going to spend some time talking about it. Okay, so um, one thing that we kind of didn't have time to discuss last time when we began to talk about sharding was there's the notion that there might be different ways to shard your data depending on how it's being accessed. So we didn't really talk about this because we didn't necessarily talk about data that's being accessed in different ways. We were just talking about key value stores. But this is actually a very important question because data might have different access patterns depending on what you want to do with it. So we only talked about this very simple data model with keys and values, but what if you had a more sophisticated data model? And when you have that, the question of how to shard the data becomes a lot more subtle. So what I mean by a more sophisticated data model might be, what if you have a relational database with kind of more sophisticated relationships between tables? Then the kinds of, the way that you shard your data might depend on what kind of queries you expect to do of that data. So, for example, people who use Facebook, the website, are accessing the data in one way. But if you're a data scientist at Facebook who's trying to do analysis of the Facebook social graph, then you're accessing the data in a different way. So those two use cases, same data, right? Same graph, but very different access patterns. And so in the end, you might want to store your data in multiple different data stores that use different ways of representing and sharding the data. So technically that would be redundant, right? Because it's the same underlying data. But the differing representations make a huge difference to how long certain tasks might take. So a data scientist who's working at Facebook, who's like trying to analyze how users access the site, that data scientist, instead of having that data scientist be sad because their queries are always really slow, right? Because they're not going to make it slow for the regular users who use the site, right? Instead, what they'll probably do is have a redundant copy of the data that's differently organized, and that copy will be specifically for the data scientists to work with. So in the MapReduce paper, they have names for these different representations of data. And they call them raw data and derived data. So raw data is the authoritative version of the data. When new data comes in, it goes into some form of raw data storage. And derived data is the result of taking some existing data and transforming it or processing it somehow. So derived data might come from raw data, or derived data might come from other derived data. The most concise description of MapReduce that I can think of is MapReduce is a tool for computing derived data. So does anybody remember in the MapReduce paper, what is the first example that they give of derived data? Inverted indices, yeah. So I think, yeah, they mentioned word count also, that's right. So the first, I think, end-to-end example that they give is a word count example, and that's a really good one. We'll talk more about that. But even before that, like in sentence 1, paragraph 1, they talk about this notion of an inverted index, right? So do you all know what an inverted index is? I think this term is a little bit confusing, so let's go over it. Okay, so let's talk about search engines. So a search engine is trying to index everything on the web, right? Or as much of it as it can. So the crawler goes out and gets a whole bunch of documents. And we end up with a list of documents, right? So we have document 1, document 2, and so on. And we have words that are in those documents. And so on. So this is sometimes called a forward index. So this might be the data structure that gets built as you crawl the web. But is this data structure good for doing queries like give me all the documents that have the word Fox in them? No, it kind of sucks for that. That would be really slow, right? If this was how your data was organized. So you don't organize it this way, or at least you don't only organize it this way. You also build an inverted index, which is an inversion of the forward index. So instead of having a list of documents and for every document a list of the words in it, an inverted index is a list of words. And then for every word, the list of documents that it's in. So the word the is in both document 1 and document 2. Quick is only in document 1. Growls is in document 2. And so on. So now we have a data structure that supports fast lookup by word. There's no more information in here than there was in this one up here. It's the same information, but it supports a different way of accessing the data. That's it. That's all an inverted index is. Okay, so how would you write a program to turn the forward index into the inverted index? And this is not yet a distributed systems question. So forget everything you know about distributed systems. Forget replication, forget partitioning, forget fault tolerance, forget all that stuff that we spent the first 7 weeks on. How would you write an algorithm to turn this into this? So here's one thing we could do. All right, yeah, go ahead. What do you think? Yeah, okay. Okay, so look through. So we have the forward index, right? We could loop through all of the documents in the forward index. What do we do? For every document, we loop over every word in it, right? And we have to keep track of the word and the document ID. So we might have something like this. For each document, in the forward index, and then for each word, so first, you're going to omit those pairs of the word and the document. So this would be something like the doc1, quick doc1, and so on. And then the ones from document 2, the doc2, dog, and so on. So that would be the result of this, right? And then what do? Well, what you want is something that looks like this, right? So you have to figure out how to combine those pairs to get something that looks like that. So what you want to do is you want to combine the documents in a list for every unique word. So you've got this list of key value pairs, right, with some repeated keys, right? Some of the words are repeated. So now all you have to do is make it so the keys are unique and squash down their values to a list of values. So you want this to turn into something like this. And so on. And then we have our inverted index. So I think the name inverted index is a little confusing because it's really just like the index that you'd see in the back of a book. So it's a list of words, and for every word, it's a list of places that that word appears. We normally don't call that an inverted index. We normally just call it an index. But for people who make search engines, it's an inverted index because it's an inversion of the forward index that was made when they were scanning the web. Okay, so would you say that the process of creating this inverted index is particularly complicated conceptually? When we leave aside all that stuff that I said to forget about, replication and fault tolerance and partitioning and all that, and making stuff go fast, if you leave aside all that, was the algorithm for computing this inverted index particularly complicated? No. No, it's pretty straightforward. I'm sure any of you could write the code to do it easily with no sweat. So why are we even talking about this? Why is this even a topic of discussion in a distributed systems class? Well, because if you're doing it at large scale, then all that stuff that I told you to forget about, of replication and fault tolerance and partitioning and making sure it goes fast, when you're doing this at large scale, this becomes a distributed system problem. And you have to think about all that stuff. You have to think about fault tolerance. You have to think about partitioning. You have to think about the stuff that this course is about. So the insight of MapReduce is that the authors, Jeff and Sanjay, as well as lots of other people, they observed that a lot of the computations that they wanted to do were conceptually simple like this. But because they had to be done on huge amounts of data in a distributed fashion, the simplicity of the algorithms was obscured by the huge amount of complication of all the code that they had to do to handle the distributed system stuff. So they said, wouldn't it be great if there were a framework that allows people to write these conceptually simple algorithms and then plug them into a system that hides all of the distributed system stuff and takes care of it automatically for them. That is what MapReduce is. So, for instance, what if our forward index here, this thing that we're operating on, what if it's too big to fit on one machine? As it, of course, is, because it's a forward index of every document on the web. So it's too big to fit on one machine. So some of our rows are on one machine, and some are on another machine, some are on a third machine, and so on. And let's also suppose that the finished inverted index is also too big to fit on one machine. So that's normal for a MapReduce computation. So what do? Let's say that you're a machine and you only have part of the forward index. So maybe you have, just for the sake of discussion, let's say that you just have this one document. How do you proceed? What do you do? Can you do anything if you just have that one document? Can you make any progress? So it turns out that you can. So you can just go ahead and compute your Word document pairs, right? You can do this for the part of the input that you are responsible for, and other machines can compute theirs for the part of the input that they're responsible for. So, in other words, this part of the outer loop, this outer loop here, this for each document, this could be done in parallel for all the documents. Even if there were only one document per machine, that's not how it's going to be. It'll be like many documents per machine. But it could be done in parallel for all the documents. Is there any dependency between the different iterations of this loop? That is, do we care about what order the iterations of this outer loop runs in? No, there's no dependency. So they're completely independent. We call computations like this embarrassingly parallel. That is to say, it is so easy to split up the computation into independent parallel tasks that it would be embarrassing not to. So there are a lot of things, of course, that are truly very hard to parallelize. But this ain't one of them. Okay, so let's imagine that every row of the forward index, that is, every document, is on its own machine. So let's draw a picture of what that would look like. Okay. And let's say that we have 3 machines at least. I don't actually have a dog. More's the pity. Okay, so in this embarrassingly parallel computation, each machine is going to run the same function on its piece of the forward index. And it's going to write the results to its own local memory. So no communication between machines is needed to do this. So machine 1 will operate on the document that it has, and it'll create these pairs of a word and a document. In this case, all the documents are going to be document 1, so it'll look like and so on. And machine 2 will do the same. Machine 3 will do the same. The results of this computation are called intermediate key value pairs. Intermediate because we're not done yet, right? We still have to create the inverted index, but this is the halfway done point. One important thing to point out is that this all happens just on these local machines. So there's no communication between the machines required to do this. And when they produce their output, they're not sending it to another machine yet. They're just writing it locally. So these are all local writes, which means they're cheap. Nothing has to be sent over the network to do this. Okay, but we're not done, right? We want to finish creating the inverted index. So what has to happen with the intermediate key value pairs now? If you have these, and what you want is something that looks like this, where you have a list from word to list of documents where that word occurs. Somebody tell me what has to happen with these intermediate key value pairs. Yeah, we got to put them together somehow. Well, the ones with the same key have to be combined, right? How are we going to do that? They're still on different machines. Well, let's say that we have two machines for this second phase of the computation. So what's going to be a good way to split up the intermediate data onto those two machines? As a hint, we talked about it a little bit last time. When we were talking about sharding. Yeah, you're going to hash the keys, right? And do, because we have two machines, we're going to do mod 2 of the hash. Or in general, if you have R machines for this phase of the computation, you can take the hash of the keys mod R. So this, if you do that, that will have the happy outcome of putting everything with the same key on the same machine. So if these were the pairs that you ended up with on your on these three machines, now you have to move them to the machines where they belong. Let's suppose that the key the hashes to machine R1. So that means that both of these will end up on machine R1. So we'll have the doc1, the doc2. And let's say that dog hashes to R1 also. And probably some other stuff. And then maybe some other keys hash to R2. And so on. But we have this nice property that everything that has the same key ended up on the same machine. Now what do R1 and R2 have to do with their data? Well, they just have to combine the pairs with the same key. So this turns into and then down here, maybe we also had something like that. So we get so that's it. So how did this data get onto R1 and R2 for them to be able to do this computation? Well, they had to get it from those machines M1, M2, and M3, right? So they had to get it from here. And this is a little bit annoying because take R1, for instance. Which machines does it have to read from? Well, it has to read from all of them, right? Because all of them might have the keys that are in the set of keys that it's handling, right? And likewise, R2 has to read from all of M1, M2, and M3. So we have a communication pattern that looks like this. So a read has to happen here. For all of those. Or if you wanted to, you could draw the arrows the other way as well. Now, fortunately, once the data is actually on R1 and R2, then they can communicate independently from each other without communicating. But you do have to have this all-to-all communication. This pattern is known as a shuffle. So I call this a communication pattern rather than a computation pattern because no actual computation takes place here. It consists only of moving data around. But this ends up accounting for a large chunk of the time that it takes to do these kinds of MapReduce computations. So computation happens locally on M1, M2, and M3, which we saw. And then computation happens locally on R1 and R2, which we saw. But then there's this middle phase where no computation is happening, but data is just getting moved into the place where it needs to be. And I guess we should draw these arrows both ways because the data gets sent to R1, R2. So shuffling is expensive. It requires sending a lot of data over the network for the sole purpose of getting it into the right place in order for the next phase of computation to happen. The good news is that you can play tricks to avoid having to shuffle so much data, which we'll talk about a little bit next time. But just to make this picture more obvious, let's flesh out the details a little bit. So we started with M1, M2, M3 with our documents over here. So here's the local part of the computation that happened on M1, for example. So that turned into this. And then similarly for M2. And so on. So that's computation that's happening locally on these machines. Then a whole bunch of data gets sent over the network, which is the result of these computations. And then when it arrives over here on these machines, they take the data that they got and they operate on it locally to produce the inverted index that we want. So there's the thing that we finally wanted. Okay, so what have I left out here? Well, I talked about how the input was too big to fit on one machine. Well, the output is also too big to fit on one machine. What's going to happen with this data once R1 and R2 are done? What happens with it? Well, R1 and R2 have to write their output somewhere. At Google, what they do is they write it to a distributed file system. So that used to be something called GFS, or Google File System. They have a new one now, but in this paper it's GFS, so let's say GFS. So R1 and R2 write their output onto GFS. So this might be like file 1. And then you might have another file that was the result of whatever R2 did. And that's it. Congratulations, you know MapReduce. So we just walked through a typical MapReduce computation. The part of the computation that took place on these machines over here is known as the map phase. Moving the data from the M machines to the R machines is known as the shuffle phase. And the part that took place on the R machines is the reduce phase. So this particular example was an inverted index, but it turns out that this pattern of map phase, shuffle phase, reduce phase is common to a lot of computations. The only part of the computation that was specific to this particular task at hand was a tiny little piece of code, right? The tiny little piece of code that we kind of sketched out earlier. So here's the tiny piece of code that was specific to this phase. So that's called the map function. And then the tiny piece of code that was specific to the reduce phase would be something like combine the documents in a list for every unique word. So everything else isn't specific to this task. So what MapReduce is a framework for doing these kinds of computations. In the MapReduce framework, you plug in these two little pieces of code, which are known as the map function and the reduce function. I'll try to write down reduce function here. Just so it's all on one page. So in order to use MapReduce, you have to plug in these two tiny pieces of code, and the rest is handled for you by the framework. It will split up your input data onto the M machines, known as the map workers. You have to specify how many you want, maybe. But it'll split them up for you. It'll put your code on all those machines so that your code that you wrote can run on the data. It'll handle the shuffling for you so that you get the correct intermediate key value pairs onto these R machines, known as the reduce workers. And it'll make sure that the output of the reduce workers ends up on a distributed file system. In the case of this paper, GFS. And by the way, everything on GFS gets replicated. So you actually use up twice as much output storage as the output that your computation produces if your replication factor is 2. So it's a lot of storage space. So that's MapReduce. MapReduce has a popular open source clone, by the way. Does anybody know what it's called? Hadoop, yeah. Uh, and of course, MapReduce depends on the existence of something like GFS. So Hadoop has its own clone of that too. It's called HDFS, Hadoop Distributed File System. Okay, let's pause and do a quiz question. And let's talk about the last couple of quizzes also. Okay, so I don't think we talked about this one yet. So the last couple of quizzes, this was from a couple of days ago. What problem does the Dynamo paper use a gossip protocol to solve? What we were looking for here was, so we talked about how Dynamo uses gossip to communicate between replicas to resolve conflicts in the view of membership. So this is distinct from resolving conflicts in the actual application key value pairs that are being stored. This is for resolving conflicts in the view of who's participating in the system. That's what Dynamo uses gossip for. So that was that quiz. This one from our discussion of partitioning. So what's the downside of using hash mod n as a data partitioning strategy? The downside is what if n changes, right? So what if you want to add or remove nodes from your system? Add nodes to your system or remove nodes from your system. Then all the data has to move around. Now I just said that we could use hash mod n to partition the data onto the reduce workers, and where we take the hash of the key and of those intermediate key value pairs and then partition it onto the reduce workers. So that's okay in this context because you don't expect the number of reduce workers to change dynamically as your MapReduce job is running. So this actually works fine as a data partitioning strategy in the use case of MapReduce. But it doesn't necessarily work fine if you're doing something like Dynamo and you want to be able to dynamically add and remove nodes from the ring. So that's what we were looking for there. The downside is if n changes, then more data has to move around than is actually necessary. All right, so those were the last couple of quizzes, and here's today. It's funny, last Friday when we were using StreamYard, so StreamYard integrates nicely with Twitch, but it also changed the category of my Twitch channel from, I think I had it on science and technology, and it changed it to talk shows and podcasts. So it's still on talk shows and podcasts. So if anybody was looking at the talk shows and podcasts category on Twitch and was hoping for a talk show, I hope you enjoyed this MapReduce lecture instead. Maybe I can change that back. Yeah, okay, so yeah, good question just asked on Slack. So is MapReduce mainly used for getting inverted index in a distributed system environment? So MapReduce is mainly used for doing all kinds of computations, not necessarily inverted index. That's so this example that we sketched out um, is it's kind of a canonical example of something that you would do with MapReduce, and something that that Google was very interested in doing in an efficient and fault tolerant way. Um, but it's not, obviously it's not the only thing. So MapReduce is allows you to plug in any map function and any reduce function that you want. Often this is going to be something for processing large amounts of text data. At least if you're Google, that's what it'll be. So inverted index is one thing that you might do. But it turns out that a whole lot of common batch processing tasks can fit into this MapReduce programming model. So let me wait a couple more minutes for quiz responses to come in, and then we'll keep talking about that. All right, so let's continue. So like we just said, it turns out that a lot of tasks can fit into the MapReduce programming model. And the paper gives a bunch of examples. So in addition to this word count and inverted index examples, uh, distributed grep, distributed sort, and so on. So these are all computations that can be expressed in the MapReduce programming model. So you can think of the MapReduce framework as factoring out all the code that's common to doing these computations at large scale and making it so that you don't have to manually write that code. So the only code that you have to write is the map function and the reduce function. And if you can figure out a way to express your computation as those two functions, then, and maybe, you know, some tuning parameters that say something like how many machines to use for which phase, the map phase and the reduce phase, and a little bit of code saying where to find the input and where to write the output on your distributed file system. That's all you have to do, and MapReduce will take care of the rest for you. So what questions do people have about this? Any questions so far? Let me go back to chat here to see if there were any questions I missed. Yeah, so this is a key point. Being able to plug in code is what it's about. And so arguably this is what a framework is. When somebody talks about a programming framework as opposed to a library. So a library sort of gives you a collection of tools that you can, or a collection of pieces that you can assemble how you want. A framework is more like here's a program with a couple of little gaps in it, and we want you to fill in the gaps. For MapReduce, you're filling in the gaps with the map function and the reduce function. And then that will kick off this whole distributed, fault-tolerant, large-scale computation in a data center. So notice that like these computations are not necessarily things that are that would be hard to do if you were doing them on one machine, right? The thing that makes them hard is the fact that you're doing them on gigantic amounts of data. Oh, sorry, somebody couldn't read this. This is the word grep here. So search, like searching for a particular for strings that match a particular regular expression, let's say. So this is briefly mentioned in the MapReduce paper. Okay, so here's a question. When we were talking about sharding, we talked about how, you know, if you want to shard onto n nodes, you can take the hash of the key and then do mod n of that. Well, we said the problem with that, right, was if n changes, then all your data, or almost all of it, has to move around. And well, n could change if you decide you need more nodes to store more data or handle more throughput. And n could get smaller if nodes died, right? So we suggested using, instead of this hash of the key mod n, we suggested using consistent hashing, right? Organizing the nodes in a ring. Every node gets hashed into a particular point on the ring, and a node is responsible for the keys that are in a given key range on a certain piece of the ring, right? And when nodes join or leave, it's only the immediate neighbor that gets affected. So that's all great. But in the MapReduce paper, they say it's fine to just use hash of key mod n. And that's the very thing that we said last time maybe wasn't the best idea. So why? Why is this okay to do in the setting of MapReduce? So here's our picture again. Yeah, so I would argue that in the setting of MapReduce, when you kick off a MapReduce job, you know how much data you're working with, right? So it's not necessarily going to be a dynamic amount of data that's arriving, right? You have, in the case of the inverted index example, you have the forward index. You know how many terabytes it takes up, and so you can reasonably estimate how many machines you're going to need. You're not going to run into a situation where you're halfway through your MapReduce computation and you think, oh no, I have to add another machine here in order to handle all the data. Now, of course, there's still the possibility that a machine can fail, right? So MapReduce has accommodations for that. So MapReduce does checkpointing. It has so MapReduce is fault tolerant, right? You don't have to start all over from the beginning should there be a failure. But you don't have to deal with this situation of, in, like, let's say in Dynamo, you have your service that's up and running, accepting requests from clients, and all of a sudden you start getting a certain kind of request that you didn't necessarily anticipate. So that isn't going to be an issue in MapReduce or in offline systems generally. You know the computation that you have to do, and it's just a matter of doing it. So next time we're going to look at more examples, and we're also going to talk more about this question of fault tolerance in MapReduce and optimizations. But I want to point out that there's a few things here that I think are key that you remember. So one thing that's key is that these computations, these writes right here, these are all local. So when each of these map workers does its computation, it doesn't have to send anything over the network initially when it's computing these intermediate key value pairs. And the reduce phase, each of these reduce workers, it's doing its computation locally, and it's then storing it somewhere on the network. So there's still network traffic that has to take place when you're storing the data in its final resting place on your distributed file system. But importantly, each of these map workers can work on its own independently to produce this initial set of intermediate key value pairs. So uh, all of the work of sending things over the network really happens in this shuffle phase. So the shuffle phase is the important part in terms of network traffic. All right, so we're almost out of time for today. Next time, we're going to look at some other examples, and we'll talk more about this question of fault tolerance. Yeah, let's wrap up. Have a wonderful beginning of your week.